Okay, that wasn't as satisfying as I had hoped it would be. This thing is a little drier than I thought it was, but whatever. I'm here today to talk about trigonometric functions, particularly the relationship between the hyperbolic functions, hyperbolic trig, and the standard circular trig. There's a lot of videos on this, even like people like Zach Starr has done a really good video on this. He doesn't cover the, or maybe he does, you know, there's a chance I missed that in his video, but I figured I ought to do this as a way to basically explain away how these two functions are related. Because, well, let's write down the definitions of the hyperbolic trig functions. So we have sinh x, which is what black pen, red pen calls it, right? And I will call it that because he calls it that. Sinh x is equal to e to the x minus e to the negative x all over 2. And of course, cosh x is similar. E to the x plus e to the negative x over 2, right? But what about sine of x? What about cosine of x? And I guess what about all the other relationships? But really you can derive everything else just from these two, just definitionally. So do we have, unfortunately there isn't something as concise as this for our trig functions, our lovely trig functions. Or is there? So look, there actually is. But it requires complex analysis. Okay, that was a shitty dotted line. Oh my gosh. Okay, let me retry that. Whatever, we get 2 dotted lines. Also shitty, but yeah. There we go, that was good. So, how are we going to do this? How are we going to find an exponential definition for sine of x and cosine x? Well, what do we always do in complex analysis? Euler's formula. E to the ix equals, and if you are in complex analysis, you should know this by heart, cosine x plus I sine of x. And we're also going to need one other thing. We are going to need e to the negative x, or e to the negative ix, which, if we plug in the argument here, is just negative x. So, since cosine's an even function, this is going to stay the same. Since sine's an odd function, the negative will come out front. Okay, so we have this here. And what I'm going to do is I am going to just add these two together. So we're going to get e to the ix plus e to the negative ix equals, well, this is going to kill, these two are going to die, so we're going to get then 2 cosine x. And very quickly realize from this that, I guess this is going to get in the way. Here, cosine x is equal to e to the ix plus e to the negative ix all over 2. Would you look at that? Now, how do we do this for sine? Well, it's pretty simple. All we have to do is just swap the signs a little bit. We can just add a negative in front. So we're going to get same thing here. We're going to have e to the ix and we're just going to add a negative sign up front. So it's going to be negative e to the ix. That's what we have. And now we can derive from this, of course, just that I sine x. We're going to add these two. These die. We're going to get e to the ix minus e to the, that should be a negative, e to the negative ix equals 2 I sine of x. And, oh, I don't want to get in the way again. Let's go around. Woo! We can, from there, look at that arrow. Wow. This is equal to e to the ix minus e to the negative ix all over, not 2, but 2i. Would you look at that? Now, this inherently shows that we can define, of course, all of these functions in terms of exponentials. Of course, the difference here is that we have an imaginary component, right? And from this, what we can really derive, and we could go the other way around. So I'm actually going to get rid of the arrows because this is where I planned on writing this, but looks like that's going to get in the way. Looks like the arrows will get in the way, so bye-bye arrows. Let's do the same thing, but we're going to swap it. We're gonna define the exponential in terms of the hyperbolic functions. Now, it's a little bit harder, but it's pretty much the same thing. We have sin x and sinh x and cosh x. We're literally going to add these together. So I will do that addition right here. So we're going to have sinh x, and this is going to be sloppy because I don't have much room, but sinh x plus cosh x, this is equal to, this is separate. Come on, dotted line, there we go. This here is then equal to, well, these we're going to add, and they're all over 2. This is going to be e to the x minus e to the negative x plus e to the x plus e to the negative x all over 2. Of course, these cancel out. And we're going to just be left with e to the x equals sinh x plus cosh x. Very similar to Euler's formula. In fact, it's literally another identity for, it's just an identity for e to the x, but without the imaginary component. And you might have actually done this part in Calc 2 because there are no complex numbers, but this is really to show how similar, particularly when relating to exponentials, and of course there's stuff with hyperbolas and circles as well, but this here really shows just how similar in behavior these two types, the hyperbolic and the circular trigonometric functions are. If you liked the video, I don't know, tell me you liked it in the comments. I don't really care if you like it. Or I don't care if you like it, press the like button. It doesn't matter to me. I'm just here having fun drawing dotted lines, showing things with math. And I better stop doing this, otherwise I'm going to forget to end the video. I hope you have fun with this. Bye!